Hey everyone, welcome back to the sorting series. And today we are going to look at one of the simplest sorting algorithms called the insertion sort. So, first, I am going to tell the intent of this sorting algorithm. So, the intent is it is same like playing cards, where when you have a deck of cards and the cards which you got needs to be sorted, you pick one card out of your hand and place it in the sorting order. Then you pick another card from the hand and place it back in the sorting sorted hand. So then your sorted hand has cards which are always sorted. So when you pick the first card, you have one card which is sorted. When you pick the second card and place it, then you have two cards which are sorted. In the third iteration, you pick another card and place it so that all these three cards are sorted. This means that at every ith iteration, you have I cards or I number of cards which are sorted. So let's visualize this. Let's say you have a list of cards. Let's say this is your list of cards. Okay. And let's say this is your sorted list. This is not the actual algorithm. We are going to discuss how actually it works, but this is just a high level visualization so that you have a better understanding of how insertion sort work. So in the second iteration, we are going to pick the first card and place it in the sorted hand. So this comes here. Then the third iteration, it is exactly like when you play cards. You pick three and you check in your sorted hand where this three should be placed. This means 3 needs to be placed just before the value 4. So this means 4 needs to move here and make space for 3. So then the 3 goes here and 4 goes here, right? Then in your fourth iteration, you check for 1 and you see, you compare 1 with 4. 1 is smaller than 4, so 4 needs to move to the right. So 4 will go here. Then you check and compare with 3, and 1 is smaller than 3, so 3 moves to the right, and then 1 comes here. Right? Now in the next iteration, we again do the same thing. 2 is compared with 4, so 4 needs to move right. 2 is compared with 3, so 3 needs to move right. So we are going to do comparisons until we find a number which is smaller than our current value. So now we found 1 which is smaller than our current number. So 1 will retain its place, and the space which is left is 2 is going to take its place. Right? So I think that's how we place cards in a sorted deck when we play a game of card. Right? Okay. So let's look at insertion sort more formally. So let's look at the same list. Now insertion sort is in place, which means the sorting is going to take place in the same array. It is stable. Okay. What else? Comparisons. And these two we are going to look later. Yes. Yes. Okay. Let's see. So we start with index second. Okay. And this is our sorted index. And this is our current index. So current index is compared with the sorted index until we find a number which is smaller, or we reach at the very beginning of the array. So we compare 4 and 3, and 3 is smaller, so we are going to do a swap. Right? Now we have sorted until here, and our current index is here. Now what we are going to do is we compare these two, and if it is smaller the number at current index, we are going to do a swap. So it is smaller, and 4 will come here, 1 will come here. Right? After that, we do a comparison of these two. One is smaller, so we need to do another swap. Okay. After this iteration, we have sorted the array until here and our current index is here. Okay. So if you see, green is representing an outer loop I, which is incrementing one at a time. And for every I, we compare all the elements until where the sorting has already been done. So when we were here, we compared these two. When my I was here, we compared these, right? Now my I is here. What I'm going to do is compare this 2 with this, then with this, then with this, right? So let's see. Comparing 2 with 4, we are going to do a swap. Okay. Then comparing, so we compared these two. Now we are going to compare these two. So because 2 is smaller than 3, we are going to do a swap, right? And then we are going to compare these two. Because 2 is greater, we not swap, but there is a comparison. And after that, we reach here and our sorting reached here and we break the loop, which means we are done. Now if we see, initially our I is equal to 1 and how many comparisons we did? From 1 to 0. In second iteration, our I is 2 and we did how many comparisons? This comparison and this comparison. So we did comparisons from 2 to 0. Then is the next iteration, our I was here I think we made a okay, right. I was here and this was our first comparison and then this was our second comparison for I is equal to 2, right? After that, I is equal to 3 and we did 3 comparisons, this, this and this, from 3 to 0, right? So this means for every I, we are doing I minus 1 number of comparisons, right? So comparisons are for every I, there are I minus 1 comparisons. But it is not necessary that for every comparison we are doing a swapping. For example, we did a comparison here, but we did not swap. We will only swap when the previous index is greater than our current index. Okay, so this means insertion sort do more comparisons and less swaps, right? Okay. Now, for every I, for I is equal to n, which is the outer loop, our inner loop runs n minus 1 times. Okay. This means when I is equal to 1, inner loop runs 0 times. When I is equal to 2, inner loop run 1 time. When I is equal to 3, inner loop runs 2 times. When I is equal to n, inner loop runs n minus 1 times. So the total time is 0 plus 1 plus 2 plus, right, which is, and these are n terms, and which turns out to be n square roughly, right? So this was a very high level visualization for the insertion sort and how much time insertion sort takes. So the worst case time complexity is n to the power 2. Okay. We are going to do a more formal analysis of the algorithm in our next lecture. I'm going to end this session here, and I'm going to see you in our next lecture, where we are going to look at the source code for insertion sorting and more formal analysis of the time complexity of insertion sort. Thanks for watching, and bye.